systems are shifting. Everything changes.
The Atlantic Ocean is losing its rhythm, quietly. Low, distant surf. Out in the dark North Atlantic, far from any city lights, a line of yellow buoys rises and falls in heavy black water. Their beacons blink through sleet and spray. Below the surface, instruments listen, not for whales or ships, but for motion itself. For a slow, deep pulse of warm and cold water that has been beating, uninterrupted, for thousands of years. Tonight, that pulse is weaker than it should be. A current that once roared like a buried river now moves like a tired lung. It drags warm surface water north, lets it cool, sink, and slide back south in the deep. To the sensors on those cables, it looks like a conveyor belt made of water. To the climate system above, it feels like a heartbeat. That balance is the system working as designed. You do not see this motion from a beach. You only feel its consequences. It is the reason winter rain in London falls as rain instead of Arctic ice. It is why familiar storm tracks bend the way they do, why the North Atlantic does not lock into permanent February. That is a fact most people hear and immediately forget. The buoys do not forget. They keep adding numbers, line after line of measurements year after year tracing the strength of this hidden flow. And in quiet offices from Miami to Berlin, scientists are watching those lines drift in the wrong direction. Not gently, not later in the century the way many models had politely promised. Faster, earlier, now. On their screens, the Atlantic's heartbeat is not stopping, but it is stuttering. It is slowing in ways that hint at thresholds, points where the system does not just weaken, it reorganizes. The science is clear on this. Push enough fresh water from melting ice and extra rainfall into the North Atlantic, and the dense water that used to sink there begins to float instead. That energy has to go somewhere. If this deep engine keeps fatting, winters across Europe do not just get colder, they get rewritten. Storms that used to curve harmlessly into open ocean start testing new paths toward crowded coasts. Heat builds up in other basins, twisting global weather into patterns that look less like unusual years and more like a different planet's normal. Flooding coasts, shifting storms, seasons that arrive late or not at all. None of that is guaranteed, yet the direction of travel is obvious enough that even the most cautious forecasters are running out of synonyms for concerned. For roughly the last 10,000 years, the full span of human cities, agriculture, and history, this Atlantic heartbeat has stayed remarkably stable. It may be the quiet background condition that made civilization possible. And now, in the dark around those blinking buoys, there are signs that this ancient rhythm is slipping out of human control. The question is how far it can falter before the entire climate system above it starts to change shape. So pull back from that dark patch of Atlantic, from that one blinking instrument, until the entire planet is hanging in front of you. The oceans stop looking flat. You start to see motion. A single glowing ribbon of warm water leaves the tropics near Florida, threads past the U.S. East Coast, crosses the Atlantic toward Europe, then dives, cool and heavy, into the deep and slides back south in the darkness. That is not just a current. That is a global delivery system. Scientists call it the Atlantic Meridional Overturning Circulation, or AMOC. In simple terms, it is a conveyor belt. Warm, salty surface water flows north. Colder, denser water sinks and returns south at depth. That balance is the system working as designed. Now slow it down in your mind. Not by much, just a fraction. The numbers are still enormous. This circulation moves around 20 million cubic meters of water every second, roughly 100 times the combined flow of every river on Earth. That is a fact most people hear and immediately forget. But that invisible transport quietly shuffles heat and salt around the Atlantic, deciding which coasts feel mild and which feel brutal. You live inside the consequences of that motion every day, whether you know it or not. Western Europe's relatively warm winters compared to Canada at the same latitude lean heavily on that northbound stream of heat. The background state of Atlantic hurricanes, the waters they form over, the steering winds that guide them toward or away from land, is shaped by how and where that heat is parked at the surface. Rainfall over the Amazon and West Africa, the timing and strength of monsoon systems, even the average sea level along the U.S. East Coast are all tied, indirectly but powerfully, to this one circulation. Change the conveyor and you change the script. That energy has to go somewhere. The science is clear on this. Multiple lines of evidence now show the AMOC is weaker than at any point in at least the last 1,000 years. Paleoclimate clues in ocean mud, coral records, and modern measurements all point the same way. Since the mid-20th century, the system appears to have slowed by roughly 10 to 20%. Imagine your heart doing that over a few decades and calling it probably fine. So what happens if the slowdown continues? What does it mean for your winter, your coastline, your food? Models and past climate shifts suggest colder, stormier winters for much of Europe, even as the rest of the world keeps warming. Sea level along the U.S. East Coast could jump faster than the global average, pushing high tides higher into streets that already flood on clear days. Monsoon rains that farmers in the Amazon and West Africa depend on could arrive late, fail more often, or swing between drought and deluge. Marine ecosystems in the North Atlantic, from plankton to cod, face a moving target of temperature, nutrients, and oxygen. Fisheries that have anchored coastal economies for generations could find the fish simply not there. And these are not distant science fiction scenarios. Early versions of them are already showing up in the data, in the weather, and in the water. The real fear is not just more change, it is a threshold. The real fear is not just more change, it is a threshold. Pull back to the map of the Atlantic for a moment. That glowing ribbon of warm water running north from the tropics looks abstract, almost peaceful. Then drop down fast into a European city in January. The trees are bare, the sky is low, and instead of snow piling against old stone buildings, a cold rain falls for the third week in a row. That is a fact most people hear and immediately forget. Northern Europe is as far north as parts of Canada, yet it rarely feels like it. That balance is the system working as designed. The AMOC ferries tropical heat across the ocean, releases it to the air, and turns what should be subarctic into something merely gloomy. Change that conveyor, and you change the heating system for tens of millions of homes. Now jump across the ocean, a U.S. East Coast boardwalk at high tide. The water already laps at the lower steps on a calm day. Add a storm surge, a full moon, and a few extra inches of sea level from a slowing AMOC piling water against the coast, and suddenly the 100-year flood is visiting every decade. Flood insurance premiums climb. Some policies vanish. The ocean is no longer a view, it is a line item. Then the camera cuts to West Africa. A farmer stands at the edge of a field that should be green by now. The soil is cracked. The seasonal rains are late again. The same Atlantic system that warms European winters also helps steer rainfall toward the Sahel and the Amazon. Nudge the currents, and the monsoon belt can shift just far enough that crops fail, food prices spike, and migration becomes less a choice and more an exit strategy. This episode is going to follow that Atlantic conveyor from the equator to the Arctic and back. From the warm surface waters off Brazil to the deep, cold return flow sliding silently along the ocean floor. Because what happens thousands of kilometers away in a basin you will never see from above the surface can decide your winter heating bill, your summer flood risk, and the price of bread at your local store. The path is simple, even if the physics are not. First, how this Atlantic conveyor belt normally works, and why moving 20 million cubic meters of water per second keeps the climate's energy budget in balance. Then, what is changing? The meltwater from Greenland, the freshening of the North Atlantic, the early warning signs that the circulation is already weaker than at any point in at least 1,000 years. Finally, what the latest science says about tipping points, timelines, and real-world risks, from abrupt regional cooling to accelerating sea level rise. The science is clear on this. That energy has to go somewhere. If the Atlantic stops carrying it north the way it used to, the weather patterns that governments, insurers, farmers, and city planners rely on will start to misfire. The tone here is urgent, but the pace will not be frantic. There will be deliberate slowdowns at the key concepts: density, overturning, feedback, collapse. Think of it as a guided tour through a failing machine that you happen to live inside. And just ahead, the first stop on that tour: how an invisible river of warm water once made the North Atlantic one of Earth's great climate stabilizers, and how scientists realized it was starting to falter. This is the moment where the scale of the problem can start to feel too big to hold in your head. An invisible river, 20 million cubic meters of water per second, quietly weakening under a warming sky. That is a fact most people hear and immediately forget. Do not forget this one. The slowdown of the Atlantic overturning is not just another climate headline. It is one of the defining climate stories of this century, because it sits upstream of almost everything else: European winters, Atlantic hurricanes, African and Amazon rainfall, fisheries, even how fast sea level creeps up along major coastlines. When this system changes, the background conditions for daily weather and long-term planning change with it. So this video is not a doom montage. It is a guided explainer built to walk through the complexity without drowning in it. Fast where it can be, slow where it has to be. When a new AMOC paper drops in 3 years with a terrifying graphic and a paywalled abstract, this is meant to give you the tools to read past the headline, to know the difference between a natural wobble and a genuine tipping point signal, to understand what scientists and forecasters actually mean when they say collapse risk. Because this system is already behaving in ways models once pushed far into the future. Multiple reconstructions now suggest the AMOC is weaker than at any point in at least 1,000 years. Freshwater from Greenland melt and heavier rainfall is pooling on the surface, making the North Atlantic lighter, less willing to sink. That balance is the system working as designed. What happens when that balance keeps shifting year after year? Longer-form investigations like this do not just appear out of warm water and concern. They take weeks of reading dense papers, cross-checking numbers, building visuals that actually show how the ocean moves beneath the surface. That energy has to go somewhere. Here, it goes into turning a huge, abstract circulation pattern into a story you can follow and remember. If this kind of in-depth, cinematic breakdown feels worth your time, consider tapping like and subscribing. It is a small action, but it tells the algorithm this system matters. It pushes the video in front of more people who have never heard the words Atlantic meridional overturning circulation, and probably never will unless it fails. That engagement also directly decides whether future episodes on other climate tipping points happen. Ice sheet instability, Amazon dieback, monsoon shifts. The science is clear on this. None of these exist in isolation. Right after the title card, the complexity gets stripped down. No jargon, just the simple physics: warm water, cold water, salt, density, gravity. First, the ocean as a machine. Then, the moment the machine starts to grind. Stay close, we begin now. Title card: THE Atlantic's hidden engine. Music shifts from tense to low, pulsing, almost mechanical. Forget the crashing waves and postcard beaches for a moment. The Atlantic is not scenery. It is hardware. It is the main heat engine for the climate you live in, quietly absorbing more than 90% of the excess energy trapped by greenhouse gases and moving that heat around the planet. That energy has to go somewhere. Most people picture global warming as air getting warmer. Thermometers, heat waves, red blobs on weather maps. But air is light. Water is heavy. The ocean can hide an enormous amount of heat below the surface, and the Atlantic is one of the primary places that heat is taken in, stored, and then shipped north like cargo. Here is the simple, slightly uncomfortable truth. Without the Atlantic's heat transport, much of northern Europe would feel more like southern Canada, even at the same latitude. London lines up with Calgary. Paris lines up with Quebec, yet winters along the North Sea are, so far, dramatically milder. That is a fact most people hear and immediately forget. The reason is not magic, it is motion. Warm, salty water flows northward near the surface, giving up heat to the air above. That heat helps keep European winters relatively soft, Atlantic storms relatively organized, and Arctic sea ice held back from the shipping lanes. Then, after cooling, that same water becomes dense enough to sink thousands of meters down and flow back south in the deep ocean. A global conveyor belt. In technical terms, the Atlantic meridional overturning circulation. Do not think of the ocean as a flat, blue backdrop. Think of it as a living conveyor system, constantly trading warm for cold, salty for fresh, surface for deep. That balance is the system working as designed. Heat moves from the tropics toward the poles, cold water returns, and the climate settles into a relatively narrow range that agriculture, cities, and power grids have learned to expect. Now here is the pattern interrupt. That conveyor is not fixed in place. It is not guaranteed to keep running just because human civilization built around it. Freshwater from melting Greenland ice and increased rainfall is making parts of the North Atlantic less salty. Less salty water is lighter. Lighter water does not sink as easily. When the sinking slows, the entire engine begins to lose power. This is not just about a gentle slowdown stretched over centuries. The science is clear on this. Complex systems that rely on delicate density differences can hit thresholds. Push a little harder, add a little more heat, a little more melt, and suddenly the response is not gradual anymore. Small extra pushes stop producing small, tidy changes. They produce jumps. Abrupt shifts in regional weather, sea level, and storm tracks. Winters in Europe that lurch colder even as the globe keeps warming. Atlantic hurricanes feeding on strange temperature contrasts. Coastal flooding along the eastern United States rising faster than any planner's comfortable spreadsheet. So the engine that has made the North Atlantic feel stable is slowing, and it may be edging toward one of those thresholds. The next step is to open the machine, watch it run in detail, and see what the warning signs actually look like. So what is this engine exactly once you open the casing? Imagine the Atlantic not as a flat blue map, but as a three-dimensional machine, a giant saltwater conveyor belt stretching from the tropics to Greenland and back again. Very slow, very steady, moving about 100 times more water than all the rivers on Earth combined. Picture a bathtub the size of an ocean with an invisible escalator running through it. Warm water rises in the tropics, glides north along the surface, sinks in the icy north, then creeps back south in the deep dark. That is the Atlantic meridional overturning circulation. That is a fact most people hear and immediately forget. Start at the sunlit tropics. There the Atlantic's surface is warm, light, and buoyant. Warm water expands, becomes less dense, and floats near the surface. Colder, saltier water is heavier. It wants to sink. That simple contrast in density sets up a pressure difference, and over huge distances that pressure difference becomes motion. A slow overturning loop. A planetary escalator. On the surface, you know part of this loop by name. The Gulf Stream. A ribbon of warm water races northward from the Caribbean and along the U.S. East Coast before bending toward Europe. As it moves, it releases heat into the air, especially in winter. That energy has to go somewhere. It pours into the atmosphere, feeding storms, softening European winters, and making cities like London far milder than their latitude deserves. Then the machine does something dramatic that you will never see from a ship's deck. Near Greenland and the Nordic seas, brutal cold and high salinity team up. Evaporation leaves the remaining water saltier. Arctic winds strip away heat. The surface water becomes so dense that it can no longer float. It plunges. This is not a gentle sink. It is a massive downward waterfall of cold, salty water, thousands of meters deep, spreading out and flowing south along the ocean floor. That deep return flow is the hidden half of the conveyor belt, sliding past the mid-Atlantic, undercutting the tropics, eventually rising again in far-flung upwelling zones. That balance is the system working as designed. You feel this invisible engine in everyday life, even if you never think about it. Shipping routes use predictable currents to save fuel and time. Fisheries in the North Atlantic depend on nutrient-rich deep water that ultimately traces back to this overturning. Coastal communities from Florida to France have built ports, housing, and flood defenses around the climate patterns. This circulation has stabilized for thousands of years. So what happens if the escalator slows or skips a step? What does it mean if the part that sinks near Greenland stops behaving? The science is clear on this. Once you understand how the conveyor belt should run, the early warning signs of failure start to look a lot less abstract and a lot more urgent. You cannot just lower a giant flow meter into the Atlantic and watch the planet's conveyor belt tick along like a factory line. The AMOC is invisible. It is a moving pattern in warm and cold water, a difference in salt and density, a pressure field stretching from the surface to the deep. So scientists have to catch it by its shadow. That shadow starts at 26.5 degrees north. Picture a line from Florida to Africa. Along that line, anchored to the seafloor, sits one of the most ambitious observing systems ever built for the ocean, the Rapid Array. That is a fact most people hear and immediately forget. But it is the closest thing to a speedometer for the Atlantic's overturning circulation that exists on Earth. Each rapid mooring is a vertical spine of instruments. They sit in darkness, feeling the water slide past. Temperature sensors track where the warm surface layer ends and the cold deep layer begins. Salinity sensors watch how fresh meltwater and salty subtropical water mix. Pressure gauges measure the weight of the entire column. From those three ingredients, scientists reconstruct how much water is flowing north at the surface and how much is plunging southward in the deep. The array does not see current directly. It infers it. Statement first, diagnosis second. In technical language, this is a geostrophic estimate of overturning strength. In plain language, it is like listening through a wall and reconstructing an entire conversation from muffled voices and footsteps. Above that invisible line, satellites are watching too. Radar altimeters on orbiting platforms scan the ocean surface, measuring sea level height to within centimeters. A small bump in sea surface height can signal a pileup of warm water. A dip can reveal a tongue of cold, dense water sliding beneath. Over years, those subtle ridges and valleys in sea level map out shifting currents, including the pathways that feed the AMOC. Then there are the Argo floats. Thousands of autonomous probes drift through the global ocean, diving down, rising back to the surface, and calling home by satellite. Each profile captures temperature and salinity from the surface to about 2,000 meters. The Pacific gets a lot of attention, but the North Atlantic is where these profiles reveal whether the water is dense enough to sink. That balance is the system working as designed. When the density drops, that energy has to go somewhere. For the deeper past, scientists turn to paleoclimate archives. Sediment cores from the Atlantic seafloor contain tiny fossil shells whose chemistry encodes the temperature and nutrient content of the water they grew in. Ice cores from Greenland and Antarctica trap bubbles and isotopes that track how the climate system responded when the AMOC slowed or lurched in the past. Those layers show abrupt shifts, sometimes within decades. Here is the tension. RAPID has only been running since 2004. Direct AMOC measurements span barely 2 decades. The science is clear on this. For a system that may take centuries to flip states, that is a terrifyingly short movie of a very long story. So the question hanging over all these instruments is simple and very uncomfortable. What if the real plot twist has not shown up on the screen yet? So scientists do something slightly uncomfortable. They zoom out, using data from a time before anyone could measure the Atlantic's pulse directly. On screen, the Rapid Time series appears, a jagged blue line of AMOC strength since 2004, swinging up and down like a heartbeat under stress. Year to year, it looks chaotic. Some winters the current surges, some summers it sags. But when you smooth the noise, a faint slope appears, tilting downward. Not a cliff, a slow lean, a modest but real weakening over just 2 decades. That is a fact most people hear and immediately forget, because a few percent change in an invisible underwater current does not feel like a headline. Yet for a system moving about 20 million cubic meters of water every second, a few percent is an Amazon river's worth of flow quietly missing from the northward stream of warmth. But the ocean has layers, and this is where the story gets older. Direct instruments only go back to 2004. Climate does not care about the convenience of human record keeping. So scientists turn to proxies and models, tiny shells in seafloor mud that record past temperatures and salinity, coral growth rings, ice cores, and high-resolution simulations that stitch those fragments together. The picture that emerges is not subtle. Multiple reconstructions point in the same direction. Today's AMOC is likely weaker than at any point in at least the last 1,000 years. Not just a bad decade, a millennium-scale anomaly in the Atlantic circulation system. Zoom in again, this time on the modern era. Many studies converge on an estimated 10–20% decline since the mid-20th century. In plain language, that means less warm water carried north, less heat released to the air over the North Atlantic, and a changed density structure in the deep ocean as fresher, lighter surface layers from rainfall and Greenland melt sit on top of heavier, saltier water. That balance is the system working as designed. Change the density, and the engine that pulls water down can start to cough. There is a visible scar of that change on the map. Global sea surface temperature charts show a world of red and orange, oceans warming almost everywhere, except for a stubborn blue patch south of Greenland. Anomalously cool water surrounded by a warming ocean. Scientists call it the North Atlantic warming hole. Models have warned about that fingerprint for years. Many associate it directly with a slowing AMOC. That energy has to go somewhere. If less heat is being carried north and vented over the subpolar Atlantic, it stays in the system, reshaping weather, shifting storm tracks, loading the dice for extremes in places that assume the old patterns still apply. So here is the unsettling question. If a 10–20% slowdown already gives you a 1,000-year anomaly, a persistent cooling hole, and a weaker Atlantic heat pump, what happens if this current is pushed much closer to its limits? For most of human history, that 1,000-year anomaly did not exist. The Atlantic's great conveyor just ran in the background, steady, invisible, dependable. For thousands of years, the AMOC has been relatively stable. Now human-driven warming is tampering with the basic ingredients that make it run. Those ingredients are simple on paper. Warm, salty water flowing north at the surface, colder, saltier, heavier water sinking and flowing back south in the deep. Heat and salt. Temperature and density. That balance is the system working as designed. Break either side of that equation and the engine starts to misfire. Start with Greenland. As greenhouse gases trap more energy, the Arctic is warming about 4 times faster than the global average. Greenland's ice sheet is melting into the North Atlantic, and the summer melt season is stretching longer every decade. That meltwater is fresh. It is light. It pours off the ice sheet and spreads across the ocean's surface like a thin, cold lens, making the upper layer less salty and less dense right where the AMOC needs water to sink. Then add the Arctic Ocean itself. Sea ice that once survived year after year is now mostly seasonal, vanishing each summer. When that ice melts, it also releases fresh water into the surrounding seas. That is a fact most people hear and immediately forget. But in the North Atlantic, a small change in salinity is not a trivia question. It is a direct hit to the circulation's intake valve. Freshwater is arriving from above in another way too. A warmer atmosphere holds more water vapor, so high-latitude regions are seeing heavier rainfall and stronger river runoff. The great northern rivers, the St. Lawrence, the Ob, the Yenisei, are quietly delivering extra freshwater to the ocean every year. It all ends up in the same place, diluting the surface in the sinking regions, making it even harder for that water to become dense enough to dive. At the same time, the surface itself is heating up. The global ocean has been shattering temperature records, not just in the Pacific, but across the Atlantic as well. Warm water is buoyant. As the upper ocean heats, it resists mixing with the colder layers below. The surface stays warm, stays light, and even in winter has a harder time cooling enough to gain the density required to sink. So the AMOC is not facing a single dramatic off switch. It is facing a slow choking of its intake. Every extra gigaton of Greenland melt, every spike in Arctic rain, every tenth of a degree of surface warming makes the deep limb a little harder to form, the overturning a little weaker. The science is clear on this. The basic physics of density are not negotiable. The only real question now is how long the engine can keep turning over as its fuel mix changes in real time. But here is the unnerving part. An engine can sputter for a long time, then fail all at once. The Atlantic overturning is not a dimmer switch that turns down smoothly as the ocean warms and freshens. It is a classic tipping system. Push it past certain thresholds of freshwater input and heat, and it does not politely slow a little more each year. It can jump. It can reorganize into a new pattern of flow that looks almost nothing like the old one. To see how that works, trade the engine for a hill. Picture a ball resting in a shallow valley. Small nudges, gusts of wind, tiny shakes make it wobble, but it rolls back to the bottom. That balance is the system working as designed. Now imagine that valley sits right next to a deeper one, separated by a low ridge. Add enough force and the ball does not wobble back. It tips over the ridge and drops into the deeper valley. In climate physics, that landscape of valleys and ridges is called multiple stable states. The AMOC has them. One valley is the strong, familiar overturning that has carried warm surface water north for most of human civilization. Another is a much weaker mode, where the sinking in the North Atlantic is feeble, the return flow sluggish, and the whole circulation pattern is locked into a different configuration that is hard to reverse. That is a fact most people hear and immediately forget. The ocean, after all, looks the same from the beach. But models and paleoclimate records agree. The ball has flipped valleys before. During the last ice age, abrupt climate swings called Dansgaard, Easter events saw Greenland temperatures jump by 8 to 15 degrees Celsius in decades. The leading explanation is rapid shifts in the AMOC between strong and weak modes as pulses of meltwater hit the North Atlantic. The most famous example is the Younger Dryas, about 12,800 years ago. As the great ice sheets retreated, a huge burst of cold freshwater likely surged into the Atlantic from proglacial lakes in North America. That energy has to go somewhere. In this case, it went into breaking the circulation. The overturning weakened sharply, the North Atlantic cooled, and Europe plunged back toward glacial conditions even as the Pacific and much of the rest of the world did not. Rain belts shifted, monsoons faltered, ecosystems and early human societies had to adapt on the fly. Those were not gentle trends, they were step changes. Today, high-resolution models show the same menu of possibilities: a stable, strong AMOC, a weaker but still functioning mode, and in some simulations, an almost fully collapsed state where deep convection in the North Atlantic essentially shuts down. The science is clear on this. In principle, the modern ocean can still cross those ridges. The argument now is not whether tipping points exist, but how close the ball is to the ridge. Some recent statistical studies of Atlantic temperature and salinity patterns claim to see early warning signals, growing flickers and wobbles that often precede a critical transition. Other scientists push back, warning that noisy data can imitate drama. So is the system merely wobbling in its valley, or already edging up the slope? The next clues are hiding in places most people never look, and what they suggest is even more disquieting. The next clue is hiding in something that sounds boring on paper: average temperature. The ocean covers more than 70% of Earth's surface. It looks calm from above, just blue water to the horizon, but it is the planet's main heat bank. That is a fact most people hear and immediately forget. A global average ocean warming of just 0.1 degrees Celsius is not a gentle nudge. It is an enormous surge of energy spread through billions of tons of water waiting to move. That energy has to go somewhere. In the Atlantic, a huge part of that movement rides on the AMOC. Warm, salty surface water flows north, gives up heat to the air, then cools, sinks, and returns southward in the deep. That balance is the system working as designed. The temperature contrast between the warm tropics and the cooler high latitudes helps drive the winds and pressure patterns that shape your daily weather. Now imagine that conveyor belt slowing. Less heat is carried north. The North Atlantic surface cools relative to the tropics, even as the whole planet continues to warm. The gradient changes, not by 20 degrees, by a few degrees here, a fraction of a degree there. But in atmospheric terms, that is like moving the rails under a high-speed train. Jet streams follow those gradients. So do storm tracks. Shift the temperature lines over the Atlantic, and the fast river of air high above you can kink, dip, or stall in new places. Storms that used to curve harmlessly out to sea can aim straight for Europe. Systems that would normally race past the U.S. East Coast can slow down and dump rain over the same river basin for days. The science is clear on this. Here is the pattern interrupt. A weaker AMOC can mean both colder snaps and fiercer heat waves over the same continent. How? Changes in the North Atlantic Oscillation. The pressure seesaw between Iceland and the Azores reorganize wind patterns. A positive phase tends to fire storms into northern Europe. A negative phase can shunt cold Arctic air south. Overlaid on that, blocking highs can park themselves over the North Atlantic or Eurasia, deflecting the jet stream and locking the weather in place. A blocking pattern is just a stuck traffic circle in the sky. Lock the pattern in and you get persistent winter cold over one region, unrelenting summer heat over another, or a stalled cyclone that turns a normal rainstorm into a historic flood. Floods in Germany, drought in the Sahel, windstorms over the North Sea. Different outcomes, same underlying energy shuffle. A subtle slowdown in deep Atlantic currents does not stay in the deep. It cascades upward, reshaping the odds of extremes thousands of kilometers away. The question now is not whether the atmosphere will notice. It already has. The question is what happens if the conveyor keeps slowing, and what else begins to flicker out of its old patterns next. So zoom out from the Atlantic for a second and look at a flat map of the northern hemisphere. Draw a line across at the latitude of London. It slices through southern Canada, brushes past Labrador, and keeps going over the endless forests of Siberia. Now look at winter photos from those places. Sub-zero cold for months, deep snow, frozen rivers. Then remember London's winters, gray, damp, mostly above freezing. Paris, Amsterdam, Dublin, all living in a climate that does not really match the coordinates printed on a globe. That is a fact most people hear and immediately forget. Geography alone says Western Europe should feel like coastal Newfoundland. The reason it does not is moving water. The AMOC hauls warm, salty water northward at the surface, where it releases heat into the air before sinking. That quiet heat transfer is why February in Bordeaux feels like a chilly drizzle instead of a survival exercise. That balance is the system working as designed. But weaken that conveyor, and the invisible subsidy disappears. Climate models that dial down the AMOC do not all agree on every detail, but the broad picture is consistent. Several degrees of cooling in parts of the North Atlantic and neighboring land. More frequent winter cold outbreaks sweeping into Western and Central Europe. A higher chance of snow in places that currently treat it as a rare inconvenience rather than a design parameter. Imagine Berlin dropping into deeper freezes more often, while Madrid sees heavier, wetter winter storms. Imagine the North Atlantic storm tracks shifting, so some years the UK is hammered by back-to-back wind and snow events, and in others, the cold air dives farther south into France and even Spain. The science is clear on this. Slow the northward heat transport, and the dice of European winter get reloaded. Here is the paradox that breaks a lot of casual conversations about climate change. Global warming continues. The planet's average temperature rises, yet some European regions could experience colder, harsher winters. Not every year, not everywhere. But often enough to feel like the old rules vanished. How do you explain that to someone staring at their frozen pipes in a supposedly warming world? That energy has to go somewhere. Extra greenhouse heat still builds up in the ocean and atmosphere, but the regional pattern shifts. The AMOC is one of the levers that decides who gets milder storms and who gets Arctic air. And those abstract shifts land in very concrete systems. Energy demand for heating jumps when cold snaps deepen and linger, stressing grids built around historical averages. Railways, roads, and roofs across much of Western Europe were engineered assuming certain snow loads and freeze-thaw cycles. Push beyond those, and maintenance stops being routine and starts being emergency response. Agriculture is tuned to familiar frost dates and growing seasons. A few days' shift is manageable. Repeated late frosts after early warm spells can wipe out fruit blossoms, stunt cereals, and scramble planting calendars from the UK to Poland. This is what a different planet can look like without anyone leaving home. The same latitude, the same cities, but winters that feel imported from somewhere much farther north. And if Europe's seasons can be rewritten by a slowing Atlantic, the question becomes uncomfortable very quickly. Whose climate script gets revised next? So if Europe's climate script can be rewritten, what happens to places that are already living right on the edge of the ocean? Picture a calm day in Norfolk, Virginia. No storm, no howling wind. Just another high tide quietly pushing water up over sidewalks that were never meant to get wet. That isn't only about melting ice and warm water expanding. It is also about the Atlantic itself shifting where it keeps the extra water. The AMOC does not just move heat, it sculpts the ocean's surface. A fast, strong current along the U.S. East Coast acts like a sideways tug, pulling water down and away from the shoreline, and piling it up farther offshore and to the north. That balance is the system working as designed. Slow that conveyor and the tug relaxes. The sea surface along parts of the East Coast is freed to creep upward, faster than the global average. Same planet, same emissions, but a different local outcome. Boston, New York, Charleston, Miami all getting an extra push of sea level rise layered on top of the global trend. That is a fact most people hear and immediately forget. But the ocean does not forget. Between about 2010 and 2015, instruments in the North Atlantic picked up a dip in AMOC strength. At the same time, tide gauges from New York to Halifax recorded a sea level jump that blindsided coastal planners. Floods that were supposed to be once-in-a-decade events started showing up every year, sometimes every few months on cloudless days. Forecasters called it nuisance flooding. Residents called it ruined basements. Here is where a few extra centimeters stop sounding abstract. Add 3, 5, 8 centimeters to a background sea level that is already higher from meltwater and thermal expansion. Then stack a king tide on top of that. Then add a nor'easter or a slow-moving tropical storm. A surge that once barely lapped at a seawall suddenly pours over it. A flood that used to stop at the curb now reaches the ground floor of homes and electrical substations. El Niño is what happens when that balance breaks in the Pacific. Along the Atlantic coast, an AMOC slowdown plays a similar role for sea level. And the built world along that coast is not ready. Aging seawalls in Boston, subway tunnels in New York, shipyards in Norfolk, low-lying public housing in Miami, all were designed for a past ocean and a past climate. That energy has to go somewhere, and in a slowing AMOC world it goes into higher baselines, longer flood durations, and saltwater creeping into groundwater and sewer lines. The science is clear on this. Combine accelerating global warming with AMOC-driven regional sea level rise, and the odds of damaging coastal floods can multiply by 10 or more within a human lifetime. So the question is no longer whether the sea will come into East Coast cities more often. The question is what happens when the Atlantic's changing heartbeat also starts to reshape the storms riding in on top of it. Those storms do not just ride in on top of a higher ocean. They ride in on top of a rearranged atmosphere, and the rearrangement starts far to the south, where the Atlantic reaches into the tropics and grabs hold of the rain. Stretch a line around the planet near the equator, and you hit one of the most important features in all of weather, a band of rising warm air and towering thunderstorms called the Intertropical Convergence Zone. In plain language, it is the planet's main rain belt. Its position and strength over the Atlantic are not random. They are steered by sea surface temperatures and by the Atlantic meridional overturning circulation itself. When the AMOC runs strong, it pulls warm water northward, shaping a subtle temperature contrast between the northern and southern tropical Atlantic. That contrast helps anchor the rain belt and the West African monsoon in a predictable zone. That balance is the system working as designed. Farmers know roughly when the rains will arrive. River basins know roughly how much water they will get. Slow the AMOC, and the pattern tilts. The northern tropical Atlantic cools relative to the south. The rain belt feels that change, and the whole band can slide southward. The science is clear on this. In models and in paleoclimate records, a weakened AMOC repeatedly shows up alongside drier conditions over the Sahel and parts of the Amazon, and wetter conditions farther south over the tropical Atlantic and southern Amazon. That is a fact most people hear and immediately forget. On the ground, it does not feel forgettable. It feels like a planting season that never really starts. Millions of smallholder farmers in West Africa depend on reliable monsoon rains to grow sorghum, millet, and maize. A shift of a few hundred kilometers in the main rain band can mean failed harvests in Niger and Mali, while fields farther south flood. The same southward nudge can starve the northern and eastern Amazon of moisture, pushing forests already stressed by heat and fire toward dieback. Pattern interrupt. This is not just about rain. It is about engines. The same Atlantic surface temperature patterns tied to AMOC strength help charge or choke the engines of hurricanes. Warmer water in the tropical Atlantic, cooler water and weaker shear elsewhere, and suddenly more storms survive and intensify on their way toward the Caribbean and the U.S. coast. That energy has to go somewhere. Sometimes it becomes a Cape Verde hurricane that scrapes along a coastline, already dealing with higher baseline seas. None of these regions exist in isolation. Drought in the Sahel, floods in coastal Brazil, and a season of intense Atlantic hurricanes can all happen in the same decade. Failed crops push food prices up. Families move. Borders harden. Political systems strain. The Atlantic's slowing heartbeat is not just a physical problem in the ocean. It is a pressure test on societies that assumed the rain would keep falling where it always has. The next question is what happens when other climate systems start to wobble in sync. When a climate system wobbles, it does not wobble alone. As the Atlantic's overturning circulation slows, those synchronized failures start to stack on top of plain old global warming. Most people still imagine climate change as a smooth ramp, a steady, predictable rise in temperature, a gradual shift in weather, plenty of time for adjustments. That is a fact most people hear and immediately forget, because systems like the AMOC do not behave like a dimmer switch. They behave like a tripwire laid across that warming trend. The background keeps getting warmer almost everywhere. Then, on top of that, Europe can suddenly swing toward harsher winters as heat transport from the Atlantic weakens. At the same time, a sluggish AMOC pushes extra water toward the U.S. East Coast, raising local sea level faster than the global average. The science is clear on this. A 1-meter rise in a model is not just a line on a graph. It is salt water in subway tunnels and over the foundations of homes that were safely above the old flood maps. Those shifts do not stay in the ocean. They move straight into food, water, and money. Altered European winters change heating demand and strain power grids designed for milder conditions. East Coast sea level spikes collide with hurricane storm surges, rewriting insurance math from Miami to Boston. Tropical rainfall bands tied to the Atlantic's warm surface waters can slide north or south, hammering one farming region with floods while leaving another to watch crops die under a blank, empty sky. That balance is the system working as designed. El Niño is what happens when that balance breaks. A weakened AMOC is another way the balance breaks, just focused on the Atlantic side of the planet. Now zoom out to where people actually live. Coastal megacities from New York and Lagos to Rio and London sit in zones directly shaped by Atlantic patterns. Low-lying deltas like the Nile, the Niger, and the Amazon's mouth already wrestle with erosion and saltwater intrusion. Add a faster regional sea level rise, and the math of staying put starts to fail. Inland, regions already on the edge of water scarcity, from northeastern Brazil to parts of the Sahel, depend on rainfall that is partly tuned by the Atlantic's warm and cool phases. Billions live inside that influence field, whether they have ever heard the acronym AMOC or not. Here is the quiet problem. Almost everything modern societies rely on was built for a different ocean. Ports, coastal highways, drainage systems, building codes, crop calendars, even social safety nets assumed that the Atlantic's conveyor belt would keep doing its job in the background. Forecasters could treat it as stable infrastructure, like bedrock. That energy has to go somewhere. As the circulation weakens, it goes into higher local seas, warped storm tracks, and rainfall patterns that no longer match the historical record those systems were calibrated to. So the physics plays out on a planetary scale, but the pain arrives one flooded street, one failed harvest, one blown-out insurance market at a time. The lived experience will be intensely local. The question now is brutally simple. How does anyone know which places are in the crosshairs next, and how close that tripwire really is? To answer that, you have to leave the flooded street and climb into the watchtower that now surrounds the Atlantic. Because long before headlines started talking about a collapsing conveyor belt, scientists were quietly wiring this ocean like a patient in intensive care. The idea itself is older than satellites, older than computers. In the early 20th century, oceanographers on wooden ships measured temperature and salinity with brass instruments and canvas buckets. They kept finding the same pattern: warm, salty water flowing north near the surface, and colder, dense water returning south at depth. They didn't call it the Atlantic meridional overturning circulation yet. They just knew the ocean was moving an enormous amount of heat. Over decades, that intuition hardened into theory. Thermohaline circulation, therma for temperature, haline for salt. Warm water moves north, cools, gets saltier, becomes heavy, and sinks. That balance is the system working as designed. The science is clear on this. Change the density of the surface water, and you change the engine of the entire circulation. But you cannot manage a planetary engine with a few scattered ship tracks. So in the early 2000s, multiple countries did something unusual. They agreed to watch the same invisible current together for decades. The Rapid Array at 26.5 degrees north, stretching from Florida to Africa. OSNAP, arching across the subpolar North Atlantic between Canada and Europe. Samba in the South Atlantic, closing the loop toward the Southern Ocean. The Atlantic quietly became one of the most instrumented basins on Earth. Picture the cross-section of that ocean as a high-tech picket fence. On the seafloor, heavy moorings hold strings of instruments that feel the passing flow and measure temperature and salinity from the surface to the abyss. Between them, Argo floats drift up and down through the water column, surfacing every 10 days to beam back profiles of heat and salt. Slender gliders fly slow, saw-tooth patterns through boundary currents, sipping battery power and sending home data by satellite. Above all of it, satellites watch the surface. Tiny changes in sea level height, mapped by radar altimetry, reveal where warm water is piling up and where it is being drained away. That energy has to go somewhere. High-resolution climate models take all of this, the moorings, the floats, the gliders, the satellites, and assimilate it step by step to simulate the overturning as it actually evolves, not just as a textbook sketch. So what is solid? The basic physics of density-driven circulation, the existence of multiple stable states in models where the AMOC can be strong, weak, or essentially off. The way freshwater from Greenland melt and extra rainfall makes surface waters lighter and chokes the sinking branch. El Niño is what happens when that balance breaks in the Pacific. In the Atlantic, a broken balance looks different, but the logic is the same. And the uncertainties, they are real. Instruments fail. Records are short. Models disagree on timing. But the alarm is not coming from one glitchy sensor or a single dramatic simulation. It is coming from the convergence. Modern arrays showing a weaker overturning, theory saying freshwater should slow it, and paleoclimate records proving abrupt AMOC shifts have happened before. That is a fact most people hear and immediately forget. The watchtower is already ringing the bell. The next question is brutal and practical. What exactly does a fatting Atlantic engine do to the climate maps everyone still assumes will hold? For years, the answer sounded almost comforting. Not yet. Most major climate models said a dramatic tipping of the Atlantic overturning was unlikely before late this century, even under high emissions. The AMOC might weaken, yes, but an outright lurch toward collapse. That was a problem for 2080 or 2100. That balance is the system working as designed. Slow, predictable change. Long timelines. Plenty of warning. Policymakers loved that answer because it meant the Atlantic could be filed under future risk instead of current emergency. That is a fact most people hear and immediately forget. But the ocean is not reading the schedule. Over the last decade, the real Atlantic has started drifting away from the script written by those models. Observational records, paleoclimate reconstructions, and updated simulations are converging on a more unnerving picture. The AMOC is already weaker than at any time in at least 1,000 years, and the pace of change is accelerating. Some studies now argue that early warning signals of instability are emerging not at the end of the century, but in this one's middle chapters. The first big outlier is Greenland. Ice there is melting faster than many earlier models projected, pouring freshwater into the North Atlantic. Freshwater is light. It dilutes the salty surface, making it harder for water to sink and drive the overturning. That energy has to go somewhere. Instead of plunging into the deep and flowing south, more of the warm upper ocean flow is stalling and spreading, reshaping regional weather and sea level. At the same time, the so-called North Atlantic warming hole south of Greenland, a patch that stubbornly refuses to warm as fast as the rest of the globe, has grown sharper and more persistent than expected. Around it, circulation patterns are doing something awkward. Jets of warm water are shifting, storm tracks are bending, and the surface temperature contrasts that steer the atmosphere are changing in ways that do not match the old timelines. Forecasters built their long-range climate maps assuming a slower decline. The ocean is not cooperating. So scientists have turned to a different toolkit, statistical early warning indicators borrowed from critical transition theory. In plain language, they look for a system losing its resilience. Recovery from natural jolts gets slower. Variability increases. The AMOC's fingerprints in sea surface temperatures and salinity are showing exactly those patterns in several analyses. The science is clear on this. That is what a system looks like as it edges toward a threshold, which leaves a deeply uncomfortable contrast. On one side, the models that said, not for many decades. On the other, an Atlantic already flashing the kinds of signals those same models associated with approaching collapse. Have the risks been underestimated, or is the real ocean simply running ahead of schedule? And what happens if planners keep trusting maps drawn for a calmer Atlantic than the one now unfolding? That split in the evidence leads to a split in the reaction. Some scientists look at the Atlantic now and see a system already leaning over the edge. Others see a noisy, twitchy ocean and warn you not to confuse a wobble with a freefall. On the alarmed end, researchers point to multiple lines of data that all seem to say the same thing. The AMOC today is weaker than at any time in at least 1,000 years. That is a fact most people hear and immediately forget. They highlight the fresh meltwater pouring off Greenland, the changing saltiness patterns in the North Atlantic, and statistical early warning, signals in sea surface temperatures that, in other complex systems, have preceded abrupt shifts. On the cautious end, other experts look at those same records and raise an eyebrow. They argue that many of the proxies for past AMOC strength, sediment grain sizes, deep sea temperature reconstructions, even coral chemistry, are indirect at best. They do not measure the conveyor belt itself. They measure what the conveyor belt might have done to the environment around it. In a restless ocean, that leaves a lot of room for misinterpretation. Then there are the models. Some high-profile studies take state-of-the-art climate models, dial in rising greenhouse gases and freshwater from ice melt, and find an AMOC collapse or near collapse later this century. Forecasters see those graphs and their stomachs drop. But modelers on the skeptical side point out that many simulations still struggle with small-scale mixing, turbulent eddies, and how warm and cold water actually blend in the deep Atlantic. If the fine-scale physics are off, the exact timing of a tipping point can be, too. The sharpest debate is over the supposed early warning indicators. In theory, as a system approaches a tipping point, it slows down in how it recovers from small nudges. That slowdown shows up as rising variance and autocorrelation in the data. In practice, you are squinting at a few decades of patchy measurements and asking whether a messy line on a graph is the heartbeat of a collapsing circulation or just the pulse of normal Atlantic weather. That balance is the system working as designed, or is it the prelude to El Niño is what happens when that balance breaks, but in the Atlantic? Recent papers claiming a likely AMOC tipping point before 2100 have landed like flares in this debate. They sparked serious engagement, detailed rebuttals, and some very pointed peer review comments. Yet beneath the argument, one conclusion runs through almost every camp. Push the climate with high emissions, and you raise the odds of crossing thresholds that are still poorly mapped. That energy has to go somewhere. The science is clear on this. The more heat the ocean absorbs, the more the entire system is forced into territory no modern society has seen before. That energy has to go somewhere, but it does not land on every coastline in the same way or on every community with the same force. A weaker Atlantic overturning is not a simple global cooling switch. It is a pattern breaker. That balance is the system working as designed. Warm surface water carried north, cold deep water flowing back south, a steady conveyor that quietly shapes the weather you grew up thinking was normal. When that conveyor slows, the map of winners and losers starts to redraw itself in real time. Parts of Northwest Europe might actually cool, even as the planet as a whole keeps warming. Picture London, Dublin, Oslo, cities that owe their relatively mild winters to Atlantic heat delivered right to their doorstep. Take away some of that heat and winter bites harder. Heating bills rise. Snow lingers. Agriculture strains. Yet at the same moment, West Africa could face disrupted monsoon rains. The Amazon could dry. and Atlantic hurricanes could draw more energy from warmer water piling up farther south. That is a fact most people hear and immediately forget. Global change sounds like one big number, but on the ground, it looks like one region drowning while another waits for rain that never comes. Now layer money and infrastructure on top of that uneven physics. A rich coastal city behind engineered sea walls, with early warning systems, backup power and evacuation routes, can take a hit from a freak storm surge and, at least for a while, keep functioning. An informal settlement on a low-lying delta, where homes sit a meter above a rising tide and the only flood plan is run uphill, lives in a different universe. A slowdown in the AMOC can raise local sea level along the U.S. East Coast faster than the global average. In Miami or Boston, that means expensive upgrades, lawsuits, bond markets getting nervous. In parts of the Caribbean, it can mean wells turning salty and tourism collapsing. The physics is the same. The outcomes are not. There are even relative winners, at least on paper. Some climate models suggest that parts of northern Europe might temporarily offset a degree or two of global warming with regional cooling if the AMOC weakens. Fewer deadly heat waves in the short term. A brief illusion of protection. But those same models show crop failures in the Sahel, forest dieback in the Amazon, and fisheries in the North Atlantic thrown into chaos. Supply chains do not care that your local winter feels pleasantly brisk. Policymakers are forced to plan inside this fog. No single forecast, but a fan of plausible futures, harsher European winters or just stormier ones, a modest sea level jump on the U.S. coast or a sharp regional spike, a slightly weaker West African monsoon or a catastrophic failure. Forecasters can narrow the range. They cannot collapse it to one clean number. And uncertainty is not a cushion here. It is a wider target for disaster. The science is clear on this. More uncertainty means more ways to be blindsided, which makes resilience and rapid emissions cuts more urgent, not less. But the real tension arrives when those uneven futures start colliding with politics, and with something even more fragile than the ocean circulation. Time. Because the Atlantic is not just a conveyor belt. It is a battery. A giant, rechargeable battery made of warm, moving water, quietly soaking up energy and freshwater changes that do not fully show up in your daily weather forecast, until they do. Every extra watt of heat trapped by greenhouse gases has to go somewhere. That energy has to go somewhere. About 90% of it goes into the ocean, and a huge share of that ends up in the Atlantic. That is a fact most people hear and immediately forget. The air feels a little warmer, the summers stretch a little longer, and it is easy to assume the system is adjusting in real time. It is not. The surface is just the blinking indicator light on the battery. The real charge is happening below. Heat is pushed down into deeper layers, tucked under cooler surface water, hidden under storms and waves. Forecasters looking only at surface temperatures are like electricians judging a power grid by the color of the streetlights. The AMOC slowdown is not just about this year's anomalies or one weird winter in Europe. It is about decades of cumulative changes in density, heat content, and stratification. Warm, fresher water from melting Greenland ice and heavier rainfall spreads across the North Atlantic surface, making it harder for that water to sink. That balance is the system working as designed. Saltier, colder water goes down, warmer water comes up, the loop continues. El Niño is what happens when that balance breaks in the Pacific. In the Atlantic, a similar principle applies on a grander, slower scale. As the density contrast weakens, the overturning circulation can reorganize. Not smoothly, not politely. A small nudge in density can tip the system into a different mode of flow. Here is the unnerving part. Deep heat storage can actually hide some of the surface warming that people use as a mental thermometer for risk. Extra energy can slide beneath the surface, into layers hundreds or even thousands of meters down. At first, that looks like a win. The weather does not explode. The headlines cool off, but the battery is still charging. When circulation patterns shift, when the AMOC weakens further, or when winds and mixing change, that buried heat can reappear quickly, driving abrupt jumps in regional sea level, storm intensity, or sea ice loss. The science is clear on this. Slow loading can produce fast impacts. That hidden loading is what keeps many climate scientists and forecasters awake at night. Not the part that is visible, but the part that is already locked in, waiting for a trigger. So far, the story has lived mostly at the surface, in currents and temperatures you can map from satellites. To understand where the real instability is building, the view has to follow the water down, into the dark, cold depths where the AMOC's return flow slides along the seafloor, and where small changes in balance can decide whether this battery discharges gently or all at once. Down there, the Atlantic is not a flat blue sheet. It is a staircase, a layered, moving cross-section of water stretching from the Southern Ocean to the Arctic, with each layer quietly doing a different job. From the side, the Atlantic looks less like a map and more like a multi-story conveyor belt, spiraling from south to north at the surface, then back from north to south in the dark. At the top, warm, salty water flows northward along the surface, helped by winds and Earth's rotation. This is the limb you feel in Europe's mild winters and along the U.S. East Coast. Beneath it, hundreds to thousands of meters down, colder, denser water slides back toward the equator, hugging the seafloor like a slow, submerged river. That balance is the system working as designed. Heat moves north, cold returns south. The ocean as a whole stays just stable enough. But that return flow does not appear out of nowhere. It has to be manufactured. The factories sit in the Labrador Sea, the Nordic Seas, and the seas around Greenland, where winter hits the Atlantic with real violence. Their brutal winds strip heat from the surface. Sea ice forms and rejects salt as crystals grow, a process called brine rejection. The water left behind turns colder and saltier at the same time, heavier, denser. At a certain point, it crosses a threshold and sinks. Plainly put, this is deep convection. The surface layer, which was floating comfortably, suddenly becomes heavy enough to plunge down several kilometers, pulling more water in behind it. Scientists call this North Atlantic deep water. It spreads southward along the bottom, undercutting other layers, carrying with it the memory of the cold sky it last touched. Here is the fragile part. Tiny shifts in temperature and salt at the surface can move that density threshold. Warm the surface by even a fraction of a degree, or freshen it with meltwater and extra rainfall, and the same patch of ocean might no longer be heavy enough to sink. That is a fact most people hear and immediately forget. But in a system this large, that small change can decide whether the factory runs at full power, idles, or stalls. When the surface becomes warmer and fresher, it floats more stubbornly. Stratification increases. In simple terms, the upper ocean turns into a light lid sitting on top of colder, saltier depths. The layers stop talking to each other. Mixing weakens. Overturning slows. That energy has to go somewhere. If it cannot go down, it stays near the surface, amplifying regional weather swings and locking more heat into the atmosphere instead of the abyss. And this is where the stakes jump from local seas to the whole planet. If deep water formation falters, the entire loop of heat and carbon storage is disrupted. Less heat and carbon get buried for centuries. More linger near the surface, where they drive storms, reshape rainfall, and push climate patterns toward new, unfamiliar states. The science is clear on this. The question now is not whether the Atlantic will respond, but how abruptly, and what signs will appear before the next shift becomes impossible to reverse. But the part that makes forecasters most uneasy is not on any satellite map. It is hidden hundreds, even thousands of meters below the surface, where the Atlantic looks calm from space but is anything but calm in reality. The deep ocean is not a quiet reservoir. It is full of slow, massive internal waves and long, rolling oscillations that move warm and cold water, salt and momentum, across entire basins. Picture invisible hills and valleys made not of rock, but of density. Layers of lighter and heavier water slide over each other, flex and pulse. That is a fact most people hear and immediately forget. Those layers have shape. In climate science, they are called density surfaces, and they tilt and wobble as winds, freshwater from Greenland, and heat lost to the atmosphere change. When extra meltwater pours into the North Atlantic, it does not just sit there like a lens on top. It bends those density surfaces, like pushing down on one end of a waterbed. The push sends a slow-moving signal along the basin, reshaping where the Atlantic overturning can sink and rise. That bending launches waves you will never see. Not surface waves with whitecaps, but internal waves and planetary waves that can be hundreds of meters tall and thousands of kilometers long. A disturbance near Greenland can send a pulse of changed density that creeps south along the deep western boundary, or sloshes eastward along tilted layers, taking years to cross the basin. A massive adjustment in the circulation. A planetary wave. Here is the pattern interrupt. The AMOC does not just flip up or down like a switch when Greenland melt increases or rainfall patterns shift. It rings. It overshoots. Internal waves can temporarily strengthen sinking in one region even as the long-term trend is downward, or they can park anomalies in mid-ocean waiting rooms where they quietly grow. That balance is the system working as designed, until it is not. Because those waves carry energy and anomalies far from where they started, the AMOC's response is delayed, distorted, and sometimes amplified. A freshening event in the 2030s could still be echoing through deep layers in the 2040s. That energy has to go somewhere. It might emerge as a sudden change in where warm water surfaces, or as an abrupt shift in sea level along a vulnerable coastline that had no obvious local trigger. If this sounds familiar, it should. In the Pacific, El Niño is what happens when that balance breaks at the surface and in the subsurface, after years of quiet charging by hidden waves. The Atlantic has its own internal signals, subsurface salinity pulses, density tilts, and planetary waves, that may act as early warnings of an approaching shift in the overturning, or false alarms that calm down just as forecasters start to panic. The science is clear on this. To see what the Atlantic will do next, you have to watch the waves you will never see. So to understand what those invisible Atlantic waves might be warning about, you have to go backward in time, to one of the sharpest climate plot twists on record. About 12,000 years ago, as the last ice age was ending, Europe was warming, ice sheets were retreating, and ecosystems were shifting north. Then in the span of a human lifetime, the trend slammed into reverse. Temperatures over parts of Greenland plunged by 5 to 10 degrees Celsius. Glaciers stopped retreating. Cold, dry winds returned. This snapback is called the Younger Dryas. On a graph, it looks fake. One moment, the climate system is climbing out of an ice age. The next, it is thrown back into near glacial conditions. That is a fact most people hear and immediately forget, but it is exactly the kind of whiplash an Atlantic slowdown can deliver. The leading explanation is brutal in its simplicity. As massive North American and Eurasian ice sheets melted, torrents of fresh water poured into the North Atlantic. Not warm, salty ocean water, the dense fuel that normally sinks and powers the Atlantic conveyor, but lighter, fresher meltwater. That fresh lid spread across the surface, like pouring a layer of oil on top of a pot that is trying to boil. Deep water formation stalled. The overturning circulation weakened. Heat that should have flowed toward the North Atlantic stayed farther south, rearranging weather patterns from Europe to the tropics. That balance is the system working as designed. The Younger Dryas is what happens when that balance breaks. Ice cores from Greenland capture this flip with eerie precision. Trapped bubbles, dust layers, and isotopes show temperatures crashing within decades. Ocean sediment cores tell the same story in slow-motion layers of mud and microfossils. The Atlantic did not politely ease into a new state. It lurched. And the Younger Dryas is not the only jump. Zoom out in those ice cores and a pattern appears. Repeated, abrupt warmings and coolings called Dansgaard Easter events. In some, Greenland warmed by 8 degrees Celsius in as little as 40 years. Between them sit Heinrich events, when armadas of icebergs dumped rock and fresh water into the ocean, freshening the Atlantic and disrupting the circulation yet again. Different triggers, same vulnerable machinery. Hit the AMOC hard enough with fresh water and the climate does not just bend, it snaps into a new mode. Today, the forcing is different. The push is not a sudden meltwater flood, but a relentless build-up of greenhouse gases, warming the whole ocean, changing rainfall, and accelerating Greenland melt from above and below the surface. Yet the paleoclimate record is unambiguous. The climate system can flip states quickly when the Atlantic circulation is stressed. The science is clear on this. That energy has to go somewhere. If it cannot ride north on a stable AMOC, it will find other paths, into shifting storm tracks, into rising regional sea levels, into new drought and flood patterns that do not match anyone's memory. So the unsettling question is no longer whether the AMOC can trigger climate whiplash. It already has. The real question is how close today's slow, human-driven push is to the kind of threshold that, in the past, the planet crossed without hesitation, and what the first unmistakable sign of that crossing will look like. So how close is that threshold now? The one past climates crossed in a geological heartbeat, sitting beneath today's warm, crowded Atlantic. Closer than is comfortable, and not nearly as clear as anyone would like. Start with the ingredients. An AMOC tipping point is not magic. It needs enough freshwater pouring into the North Atlantic to dilute the salt, enough warming to keep the surface light and buoyant, and internal feedbacks that kick in once the circulation weakens. Fresh melt from Greenland, heavier rainfall, and river runoff all act like a lid of lighter water on top of a denser ocean. That balance is the system working as designed. Dense water cools, sinks, and pulls warm surface water north. Reduce the density contrast enough, and the engine starts to cough. Then the feedbacks arrive. A weaker AMOC transports less warm, salty water northward. The North Atlantic freshens and cools at the surface, which sounds stabilizing, until it allows even more sea ice and meltwater to accumulate. That in turn makes the surface layer even lighter. The circulation slows further. That is a fact most people hear and immediately forget. But in a tipping system, that spiral is the whole plot. So are those spirals visible yet? Several recent studies have taken the limited observational record, stitched it together with model output, and used statistical tools that look for critical slowing down. In plain language, as a system approaches a tipping point, it recovers more slowly from random shocks. Variability grows. Correlations in time stretch out. In 2021 and again in 2023, separate groups argued that these fingerprints are already emerging in North Atlantic temperature and salinity patterns. In their reading, the AMOC is not just weaker, it is losing resilience. Other scientists are more cautious. They point out that the instrumental record is short, the Atlantic is noisy, and models disagree on how clean those early warning signals should look in the real ocean. The IPCC reflects that caution. Its reports acknowledge increasing risk of a major AMOC weakening this century, especially under high emissions, but stop well short of saying, the break happens in year X. The science is clear on this. The risk is rising, but the exact distance to the edge is deeply uncertain. Under the most aggressive warming scenarios, some papers place a potential tipping point between about 2050 and 2100. Others push it beyond 2100 or judge a full collapse this century as unlikely, but no longer dismiss it. That is the uncomfortable middle ground. Not guaranteed, not safely off the table. Which leaves the core dilemma. Humanity is walking toward a cliff in the fog. The exact drop-off is unknown, but the ground is already sloping. The weather is getting stranger, and the ocean's great conveyor is clearly slowing. If forecasters underestimate how close that edge is, the cost is not a bad forecast. It is a different planet. And the next question is brutal. What actually happens on the day the Atlantic finally tips? On the day the Atlantic tips, nothing explodes. No giant wave, no instant ice age, no Hollywood freeze ray rolling down Fifth Avenue. The surface looks almost normal. Ships still cross. The ocean still moves. But underneath, the conveyor has dropped into a lower gear. In most models, a collapse of the Atlantic overturning does not mean the water stops. It means the entire circulation settles into a much weaker, brutally stable state. That balance is the system working as designed. The new balance is the system working in a way human civilization has never seen. Now zoom out over the North Atlantic. Over a decade, the map of temperature anomalies starts to warp. The globe, on average, keeps getting warm, yet a cold patch blooms south of Greenland and refuses to leave. Western Europe, which has been quietly borrowing heat from the Atlantic for centuries, begins to pay it back. Winters in the UK, Ireland, Scandinavia cool by several degrees. Not one freak season, a pattern. Imagine a January in London where the rain is sleet more often than drizzle, where freezing nights are normal again, even while summers elsewhere keep smashing heat records. That is a fact most people hear and immediately forget. The planet warms, but some regions get colder. The contrast sharpens the weather. Storm tracks over the North Atlantic start to shift. The jet stream kinks and stalls more often over that stubborn pool of cold water. Deep winter cyclones spin up faster, feed on sharper temperature gradients, and hammer some coasts with stronger winds and heavier, longer-lasting rain. Other areas, especially farther south, see hurricane behavior change. Storms may form less often, but the ones that do can intensify closer to shore, dump catastrophic rainfall, or curve on unfamiliar paths. Forecast cones get wider. Insurance maps get redrawn. Beneath the surface, the biology follows the physics. Cooler, fresher surface layers and weaker deepwater formation change how nutrients are stirred up from below. Plankton communities shift in size, timing, and species. The microscopic base of the food web moves north, or peaks earlier in the season, quietly missing the arrival of fish larvae that evolved to be right on time. That energy has to go somewhere. It goes into winners and losers. Iconic North Atlantic fish like cod and mackerel chase their preferred temperatures toward the Arctic, leaving traditional fishing grounds behind. Some stocks crash outright. Others boom in new waters where the boats and the laws are not ready. Coastal towns that have pulled food and money from the same patch of ocean for generations find that the ocean has simply moved. And this is not a bad decade that then snaps back. In a partial collapse state, the weakened overturning can persist for centuries. Long after greenhouse gas emissions are cut, long after global averages stabilize, the Atlantic can remain locked into this altered mode. The science is clear on this. Once the conveyor finds that lower gear, it is very hard to kick it back up. So the real question is not just what the first 20 years look like. It is what happens when children are born into that new regime and are told it is normal, right up until the next tipping element wakes up. So the next question hits a little harder. If the conveyor is drifting toward a cliff, can anyone see the edge before the wheels go over? Or does the Atlantic change gear the way a bridge collapses in an earthquake, slow cracks, then one impossible second, and it is simply gone? Scientists are not going in blind. They are hunting for what are called early warning indicators. Plain language first. A system that is losing stability starts to wobble. Technical language, increasing variance, rising autocorrelation, and slower recovery from disturbances in AMOC-related metrics. The current begins to swing wider around its average. Each nudge from random weather lingers longer. That balance is the system working as designed, until it is not. Imagine the North Atlantic overturning as a pendulum in warm, salty water. In a healthy regime, a winter storm kicks it, the flow weakens briefly, then snaps back. As a tipping point approaches, the same storm leaves a longer fingerprint in deep water formation, sea surface density, and heat content. Recovery slows. That is a fact most people hear and immediately forget. But in the math, that delay is a siren. To hear it, researchers are stitching together everything available. Decades of mooring records from arrays like Rapid at 26.5 degrees N. Satellite altimeters tracking subtle changes in sea surface height, temperature and salinity from Argo floats. High-resolution climate models that simulate thousands of years of AMOC behavior. And now, machine learning systems trained to recognize the faint combinations of signals that tended to show up in models before a collapse. A massive pulse of fresh meltwater here, a persistent pressure anomaly there, a quiet shift in deep return flow. Alone, each looks like noise. Together, they might be the pattern. There is a pattern interrupt hiding in plain sight. Most of the Atlantic has never been continuously measured for even one human lifetime. Long-term direct AMOC data only exists since 2004. Before that, the record is stitched from ship transects and proxies like sediment grains and coral chemistry. Powerful, but patchy. Models that fill the gaps carry their own biases about how turbulent mixing works, how Greenland melt spreads, how the Southern Ocean talks to the North Atlantic. Distinguishing natural multi-decadal swings from a true approach to instability is like trying to hear a cracked gear in a freight train while standing in the engine room. So proposals are getting more ambitious. Denser mooring arrays at multiple latitudes to track the overturning in stereo instead of at a single line. Expanded Argo coverage into ice edge regions and deeper layers, so the hidden warm water and density structure are not guessed but observed. Dedicated monitoring of Greenland melt, more GPS on the ice sheet, more freshwater tracers, more coastal sensors to see how that pulse of low-density water spreads into the sinking regions. That energy has to go somewhere, and forecasters want to know where before it arrives. The uncomfortable part is the timeline. Even in optimistic scenarios, early warning indicators might only give a lead time of years to a few decades between a clear signal and an effectively irreversible transition. Under high emissions, with Greenland melt and North Atlantic warming accelerating together, that window could shrink. The science is clear on this. Foresight is possible, but it will not feel generous. So the real decision point may not be when the warning lights finally glow red. It may be whether action begins while the gauges still look, to most people, completely normal. So imagine this. The Atlantic's conveyor belt is quietly fraying in the background, and the policy debate is still arguing over whether 2.0 degrees C is worse branding than 1.5. On paper, the gauges look normal. In the water, the stress is already building. Here is the uncomfortable part. No model can give a precise calendar date for an AMOC tipping point. There is no June 17, 2073 at 4 p.m. moment. But the direction of risk is not a mystery. Higher greenhouse gas emissions mean faster warming, more Greenland melt, more rainfall, and more freshwater sliding across the ocean's surface into the North Atlantic. That energy has to go somewhere. Freshwater sounds harmless. It is not. It makes the surface lighter, less dense, less willing to sink. That sinking is the engine of the circulation. Reduce it enough and the engine stalls. The science is clear on this. More heat in the climate system pushes the AMOC harder toward its weak state, even if the exact threshold remains fuzzy. This is where emissions pathways stop being abstract curves on an IPCC chart and start looking like branching timelines. Under rapid cuts, global warming might be limited to something near 1.52 degrees C. Greenland still melts, the Atlantic still warms, but the pace slows. Models suggest the probability of crossing an AMOC tipping point this century under that pathway is lower, still non-zero, but more like a tail risk than a central forecast. Under business as usual, the story changes. Think 3 degrees C, 4 degrees C, maybe more, with the North Atlantic taking a disproportionate share of that heat. Ice loss accelerates, freshwater pours in, and early warning indicators in models flip far more often. In that world, the probability of a major AMOC disruption before 2100 stops being an outlandish scenario and becomes something forecasters have to put real numbers on. And that is the deeper policy problem. Climate decisions are not only about nudging the global average temperature graph a little lower. They are about avoiding low-probability, high-impact catastrophes, an AMOC lurch, an ice sheet cliff, a rainforest dieback. That is a fact most people hear and immediately forget. Quietly, those tail risks are already reshaping how risk is priced. Large insurers are beginning to fold tipping points into long-horizon models, even if the probabilities come with huge error bars. Military planners talk about North Atlantic disruption in the same breath as sea level rise and Arctic routes. Central banks run climate stress tests that include abrupt shocks, not just smooth warming. Notice the pattern. Every 1/10 of a degree avoided takes pressure off the system. Less warming means less freshwater, less stratification, a slightly more forgiving Atlantic. That balance is the system working as designed. In practical terms, that extra breathing room buys time. Time to expand deep ocean monitoring, to refine early warning indicators, to test adaptation plans, and to decide whether more radical technological responses should ever leave the whiteboard. The question, then, is simple and brutal. How much risk is acceptable when the downside is a rearranged Atlantic climate? The next piece of the puzzle is how that risk actually shows up in real weather, real coastlines, and real economies. Risk shows up in very physical ways. It looks like water in your subway tunnel and salt in your drinking aquifer. Along the U.S. East Coast, a weaker Atlantic circulation doesn't just mean higher sea level someday. It means the ocean surface literally bulges toward the coast as the current slows, stacking extra inches on top of global sea level rise. That is a fact most people hear and immediately forget. But those inches are the difference between a nuisance flood and a flooded hospital. Cities have 3 basic moves: fight, bend, or leave. Fighting looks like taller seawalls in Boston and Miami, surge barriers across New York Harbor, and pump systems that treat every high tide like a storm. Bending looks like raising roads, waterproofing subway vents, and allowing certain neighborhoods to flood without collapsing the whole system. Leaving is the phrase planners hate to say out loud: managed retreat. Selling homes, buying out floodplains, and admitting that the ocean has won that particular argument. Europe faces the same Atlantic, but a different flavor of risk. A weaker AMOC can mean colder, more volatile winters over Western Europe, even as the planet as a whole gets warmer. That balance is the system working as designed, until the circulation falters. Suddenly, energy demand spikes during cold snaps, wind patterns shift, and the grid is asked to be both more flexible and more resilient at the same time. Adaptation here means hardening transmission lines against ice and storms, building more interconnections between countries, and investing in storage so that when the wind and sun fail, the lights do not. It also means millions of buildings getting serious insulation, heat pumps, and smarter controls. The science is clear on this. Every kilowatt-hour you do not waste is one you do not have to chase in a crisis. Far from these rich grids, the adaptation story looks very different. In the Sahel, a disrupted Atlantic can help shift the monsoon, turning a fragile balance between rain and drought into a coin flip. Farmers respond with drought-resistant millet and sorghum, small reservoirs, and irrigation that uses every liter twice. In the Amazon basin, altered Atlantic temperatures can dry out forests that are used to warm, wet air rising from the canopy. That energy has to go somewhere. It often returns as longer dry season and more fires. Here, there are fewer seawalls and more hard choices. Wealthy ports can pour billions into concrete. Small coastal towns argue over which road to save. Northern European homes get triple glazing. Sahelian villages debate whether to send one more child to the city. Adaptation can blunt the blow. It cannot erase it. Ecosystems cannot build seawalls. The poorest communities cannot refinance their way out of a failed harvest. And if the AMOC crosses a real tipping point, the question will not be how high to build the wall, but whether the map under it still makes sense at all. So the next temptation appears almost automatically. If the map might stop making sense, why not redraw it on purpose? In the background of the AMOC debate, a quieter conversation has been growing. Not about cutting emissions faster, but about reaching directly into the Atlantic and trying to hold the circulation in place with technology. Diverting huge rivers so less freshwater reaches the North Atlantic. Building vast barriers to keep meltwater from Greenland away from key sinking zones. Brightening clouds or putting reflective particles in the sky to cool specific patches of ocean surface, like ice packs on a fevered patient. On paper, some of it almost looks tidy. A few degrees less warmth in the subpolar North Atlantic, a little more density in that surface water, and the sinking branch of the conveyor could, in theory, strengthen again. That balance is the system working as designed. Models can flip switches, dial down solar input over the Atlantic, reroute virtual rivers, and watch the digital AMOC respond. But models do not vote. Models do not fish. Models do not live downstream of a dam that just had its flow reprogrammed. In the real world, every geoengineering lever comes with uncertainty and side effects attached. Cool the North Atlantic aggressively, and the jet stream can shift. That energy has to go somewhere. Maybe winter storms slam harder into southern Europe. Maybe the West African monsoon weakens and Sahelian farmers lose the rains that were barely enough to begin with. Maybe the Amazon, already stressed, gets just enough extra drying to tip more forest into fire. Pattern interrupt. Imagine trying to fix one ocean current and discovering you have accidentally moved the band of tropical rainfall that feeds 2 billion people. There is no global undo button. Reflective geoengineering brings its own trap. Once aerosols are in the stratosphere to cool the planet, or targeted marine cloud brightening is propping up sea ice and Atlantic density, stopping suddenly can unleash a rapid rebound of warming. The system would feel not one shock, but two. That is a fact most people hear and immediately forget. And then there is geopolitics. Who decides how much to cool which ocean and when to stop? The country that fears AMOC collapse or the country that fears its monsoon failing? Forecasters can simulate scenarios, but they cannot negotiate trust between governments that barely agree on fishing rights. Most experts are blunt about the hierarchy of options. The science is clear on this. Reducing greenhouse gas emissions, slowing the melt of Greenland, restoring ecosystems that store carbon, and adapting infrastructure are far safer and more controllable than trying to re-engineer the Atlantic itself. Directly forcing the AMOC is the climate equivalent of open-heart surgery on a moving train. The fact that these ideas are even on the table tells you how high the stakes have become. But it is also a warning. When a system that quietly moved 20 million cubic meters of water per second for thousands of years starts to wobble, the first instinct should not be to grab the controls. The better question is how close those controls already are to failing on their own. For the people who watch this system for a living, that question is not abstract. It is personal. It is the moment you open a new Atlantic data plot and feel your stomach drop before your brain catches up. One oceanographer described staring at a graph of North Atlantic surface salinity and thinking, "If this were a patient, I'd call the family." Another talks about sailing past Greenland, watching warm, fresh meltwater streak the surface in turquoise bands over darker, saltier water, and feeling both awe and dread at the same time. The beauty does not cancel the fear. It sharpens it. That fear is not about guaranteed apocalypse. The science is clear on this. No reputable model says, The AMOC will absolutely collapse by Tuesday. The terror comes from something more unnerving, a range of plausible futures that includes very bad outcomes, combined with a system that does not give much advance notice before it crosses a line that cannot easily be uncrossed. Think about what the models are asking. How does a circulation that has moved warm water north for thousands of years respond when Greenland pours fresh water onto the surface like a fire hose? How does the atmosphere react if the North Atlantic suddenly stops sinking as efficiently, shuffling where heat and energy leave the ocean? These are not questions with clean, single-number answers. They are probability distributions with fat tails where nobody wants to live. That is why some scientists describe checking new simulations like opening exam results for the whole planet. Did the circulation hold? Did it wobble? Did it tip? One team's projections show a steady decline through the century. Another's show an abrupt break this side of 2100. That is a fact most people hear and immediately forget. For the people running those models, it is the reason they stay late in the lab. But the emotional story is not just dread. Many of the same researchers will tell you they are driven by hope that rapid emissions cuts and a better understanding of how heat and freshwater move through the Atlantic can keep the AMOC in its current, relatively stable regime. That balance is the system working as designed. Every fraction of a degree less warming means less meltwater, less added buoyancy at the surface, less stress on that deep overturning. They also know their words carry weight. Say collapse too loudly, and people tune out or assume everything is already lost. Downplay the risk, and policymakers keep building coastal cities and food systems on the assumption that the weather of the last 50 years will quietly continue. Communicating a threat that is both uncertain in timing and enormous in consequence is its own kind of tightrope. So as the video moves deeper into scenarios, timelines, and what can still be done, you are stepping into the same uncomfortable space scientists occupy every day, holding fear and hope in the same hand, and refusing to let either one be an excuse for looking away. So what does an unstable Atlantic conveyor actually feel like when you walk out your front door? Not as a Hollywood disaster sequence, more like your seasons quietly drifting off script. Start in Northern Europe. Maybe you live in the UK, Ireland, Denmark, or coastal Norway. Your grandparents remember winters with real snow, but your recent winters have been weirdly warm and wet. A slowing AMOC doesn't just flip that back to old-fashioned cold. It can mean harsher cold snaps dropping in without warning, more freezing rain, and a growing risk that late frosts kill blossoms that open too early. That is a fact most people hear and immediately forget. Until their food bills jump, because a frost wiped out half the local fruit harvest. Cross the Atlantic to the U.S. East Coast. From Miami condos to Boston triple-deckers, millions live just a few meters above sea level. As the AMOC weakens, warm water piles up along this coastline, pushing sea level higher than the global average. That balance is the system working as designed. Break it, and a routine nor'easter can start behaving like a once-in-a-decade flood. High-tide flooding days multiply. Storm surge rides in on a slightly higher baseline. Suddenly, the 1-in-100-year flood map taped in your town hall looks more like 1 in 20. Now look south toward West Africa. If you live in Senegal, Ghana, or Nigeria, your life might be timed to the monsoon. When to plant, when to fish, when to store water. AMOC changes ripple into the tropical Atlantic, nudging where warm surface water pools, shifting the band of rain north or south. Some years, that could mean delayed monsoons and failed crops. Other years, violent downpours that overwhelm drainage in cities already choking on traffic and aging infrastructure. The science is clear on this. Small shifts in ocean energy can mean big swings in local weather. Over the Atlantic and inland again, the Amazon basin sits downstream of these changes. A weaker AMOC can disrupt the moisture conveyor that keeps the rainforest humid. Longer dry seasons, hotter heat waves, more fire. That energy has to go somewhere. If it is not locked in the ocean, it shows up in the air above your head. No one can tell you exactly what will happen in your specific town, but plausible shifts can be outlined. Frost dates creeping later in autumn and earlier in spring, flood frequencies ticking upward, heat waves stacking closer together until the gap between them feels like the exception, not the rule. So the question quietly becomes, where are you vulnerable? Are you in a floodplain behind an old seawall, dependent on rain-fed agriculture, or living in a city where a single substation powers half the neighborhood? Local meteorological agencies and climate services are starting to fold AMOC trends into seasonal outlooks and long-range planning, even if the fine print still talks in probabilities. Because this isn't just academic. Understanding the AMOC is part of understanding why your local extremes are changing and what might come next. The real shock is what happens when those local threads are all pulled at once. So when a headline flashes that the Gulf Stream is collapsing, or a mini ice age is coming for Europe, it lands on top of that tangled, fragile web in your mind and yanks hard. It feels like everything is failing at once.